Hi everyone, we're now going on to the ionic bonding model. Okay, so in the ionic bonding model, the metal ion transferred its valence electron or outer shell electron or electrons to the non-metal atoms or polyatomic group. The metal is the positive charge or cation, the non-metal is the negative charge or anion. Now, because the cations and the anions have opposite charge, they are held together through electrostatic attraction. We can see here on the next slide, we have a lattice structure that each positive ion is surrounded by negative ions. If I pick this one here, you can see it's surrounded by 6 of the opposite charged ion. If we look at the green one, it's surrounded by 6 yellow ones. So we've got a lattice structure of alternating positive and negative charges. If we look here at these electron transfer diagrams, and you're going to need to be able to draw these, you can see we've got magnesium, 2 in the first shell, 8 in the next shell, 2 in the outer shell, and oxygen, 2 in the first shell, 6 in the outer shell. The electrons are transferred from one to the other, forming an ionic bond. But it doesn't just happen one to one, we then form that whole lattice structure, okay, as you can see here. Now, if we look here, this is a list of ionic compounds and their properties. Copper sulfate and sodium chloride. Let's just look at those two. Melting points. We run down the list, they're quite high. That tells us that the ionic bond is a strong bond. Do they conduct as a solid? No, they don't. That tells us that there are no free charged particles that can move to conduct electricity or heat. As a liquid, they all conduct heat and electricity. So when we break the bonds through heat, they are able to move, which makes sense because then you've got the free cations and anions that can move to carry the charge. Conductivity, I'm not quite sure if you can see all this. Conductivity in aqueous solution, that means when we dissolve it. Copper sulfate, sodium chloride and sodium hydroxide can, but that's because they dissolve in water. This is about solubility, how things dissolve. And you can see they dissolve quite readily, whereas calcium carbonate and zinc oxide, they don't dissolve in water. So these two can't conduct because they don't dissolve, so they can't conduct. Okay, and then where we use them. So copper sulfate is used and put on fruit to stop it from going off. Sodium chloride is used as a preservative and a flavour enhancer. Calcium carbonate, you might have marble benches at home. That is made of calcium carbonate. Zinc oxide, sunscreen, sodium hydroxide, a great cleaning agent. Okay. You can now go on to please doing some questions. Page 87, questions 1 to 4. Actually, I might keep going. We'll put them in. Here's a picture, ionic bond. The electrons are taken, not shared. All right, here's a picture of an energy transfer diagram. We already had that one. Properties, we'll keep going. The properties I think we've just talked about. Brittleness. That's the one that we didn't talk about yet. Brittleness, let's slide down to this one. Because we've got the alternating positive and negative charges, if we push them and align the positive charges together and the negative charges together, they will repel each other, and that will cause the lattice to separate. So ionic compounds are brittle. This compares with metallic compounds where we've got the cations in the sea of electrons and they can slide past each other. The conductivity we've talked about, and we've talked about the uses. Okay, thanks everybody. I'll stop the video there. Do your chapter questions.